Now we get to move on to section 3.6, which is all about factoring trinomials. Ultimately, we have seen that when we multiply two binomials together, we get a trinomial. So we want to work backward. We want to be able to turn this trinomial into a product of two binomials. I'm going to teach you how to factor trinomials through two different strategies. Again, you can choose to use whichever strategy is easiest for you. Let's go ahead and use the area model first. Think back to when we were multiplying our binomials in the beginning of chapter 3 with an area model. We ultimately had a binomial as our height and a binomial as our base. When we multiplied it together, we were able to fill in our rectangle. So, what does that mean in terms of filling in our area model? Well, the top left-hand corner should be the x squared term. We also know that the bottom right-hand corner should be the constant. Think about the other two parts of our area model though. Together, we know that they need to add to be the middle term, in this case, 5x. I'm going to go ahead and write a 5x on the outside of that diagonal, just like this. So I know that I need two numbers that would add to be 5x, but how an area model works is I also know the two numbers need to multiply to be 6. I could do 1 and 6, or I could do 2 and 3. 2 and 3 are going to work because 2 and 3 add to 5. That means I'm going to go ahead and put a 2x into one of the parts of the area model that's missing, and then I'll put a 3x in the other part. It does not matter which one goes where. It's just going to impact which factor is your base and which factor is your height. So once you have the area model set up like this, you can actually look at the greatest common factor, or GCF, of each row and column. So let's go ahead and look. The greatest common factor of our first column, x squared and 2x, is just x. So I'm going to go ahead and write an x on top of the column that it is the GCF for. Moving on to the next column, the 3x and the 6, those both have a 3 in common. So I can go ahead and I can write a 3 on top of that column, just like that. Now, I need to do the same thing for each row. So the GCF of this first row, x squared and 3x, is again x. So I can go ahead and I can write my greatest common factor of x on the outside of that row. And then I need to do 2x and 6, which have a 2 in common. I can go ahead and write a 2 on the outside of that row. Now, you can actually see your two binomials, that is our product. Up here we have an x and a positive 3, making it the factor of x plus 3. And then our height is going to be x plus 2. Therefore, x squared plus 5x plus 6 factors to x plus 2 times x plus 3. Just like that. Remember, multiplication is commutative, meaning that even if you had switched which rectangle of your area model the 3x and the 2x went in, you'd still end up with a factor of x plus 3 and a factor of x plus 2. So it does not matter the order in which you write those factors. I told you I would teach you one other way, so I'll go ahead and do that for this particular example. For all future examples, though, I do plan to use the area model. The second strategy is factoring by grouping. We would set it up very similarly, other than we don't have this pictorial representation to kind of help us out and keep things organized. So what we're going to do is we're basically going to split our middle term up, 5x, into a sum of two terms. We're looking for two values that will end up being the coefficients that multiply to 6, but add to 5. That's right, it's still 2x and 3x, just like it was in the area model. And once we have that, we can go ahead and factor by grouping. Remember, when you factor by grouping, you group the first two terms together and then the second two terms together, just like this. Now we want to look for the greatest common factor within each group. So for our x squared plus 2x, those both have an x in common. And then for our 3x plus 6, we're going to be able to pull out a 3. If you've set it up correctly, you should now have a greatest common factor between your two remaining terms. In this case, we have our x plus 2 in both the first term and the second term, so we can factor it out. And once we factor it out, look at what we're left with. If we take the x plus 2 out of the first term, we are left with just an x. If we are taking it out of the second term, we are left with a positive 3. Notice that factors to the exact same expression that we had when we did the area model. That's our final answer. X squared plus 5x plus 6 factors to x plus 2 times x plus 3. Now, those are both excellent strategies. However, we are unfortunately not going to have trinomials that easy all the time. Go ahead and look at this trinomial. 3n squared minus 7n minus 20. See if you can spot any differences. That's right, the leading coefficient is not 1 anymore. That's going to make things a little bit more interesting. Let's see how we can deal with this. We're going to start by setting it up the exact same way. Basically, our leading term, the 3n squared, is still going to go in the left-hand box. If you're doing factoring by grouping, you'd keep it as the first term. Similarly, we can put that negative 20 in the bottom right-hand box or as our final term when we factor by grouping. Now, remember, the other two spots in our area model, that diagonal, has to sum to the middle term, or the b term, negative 7n. I'm going to write that again next to the diagonal to help us keep track. Now, you may be jumping ahead and thinking, oh, I need two numbers that multiply to be negative 20 and add to be negative 7. You probably aren't going to find any if that's the case. Here's why. When we have a leading coefficient that isn't 1, that unfortunately means that we're going to have at least one of our leading terms in our binomials that are also not going to have a coefficient of 1. When you multiply things out, it unfortunately is just not going to work that this number times this number equals negative 20 and sums to negative 7. So to take that into account, we use a method that I like to call the AC method. Where that comes from is typical quadratic notation. This is a quadratic, it's a power of 2, remember, is ax squared plus bx plus c. We'll learn all about quadratics later in UMTYMP. But what we're going to do is we're going to take a times c for the AC method. You are more than welcome to do the full terms of a and c when you're doing the a times c for the AC method. I prefer to just look at the coefficients and then remember that I need to write the coefficient with an n in both of these diagonals because it has to sum to negative 7n. So we are looking for two numbers that multiply to be negative 60 that sum to be negative 7. Let's go ahead and go through some options. Because I know two numbers have to multiply together to be a negative number, I know that one of them has to be negative. Now, you could also plan ahead and think, wait a minute, if I need them to sum to a negative number, then the negative number has to be the bigger factor. That would actually eliminate a lot of options, but I went ahead and listed them all for you so that you can see where I'm getting all these possibilities from. Basically, for negative 60, I went and listed every single pair of factors. For example, 1 times negative 60 and negative 1 times 60 ultimately still multiplies to negative 60. Unfortunately, though, neither of those sets of numbers would sum to negative 7, so that's not going to work. You would work your way through this list. If it helps you, you can always go ahead and cross them off as you go. Eventually, you're going to get to the one that works. See if you can find it. Pause the video and start it again once you have found it. Hopefully, you found that 5 and negative 12 is going to sum to negative 7n. That means in one of the boxes of our rectangle or our area model, we can write 5n. And then in the other one, we can put the negative 12n. Just like this. Then, going back to how we learned about area models before, we'd be able to look at each row and column and take out the GCF, or greatest common factor. Let's go ahead and look. I'm going to look at the first column first, 3n squared and 5n. That only has an n in common. So I can go ahead and write an n on top of that column. Let's go ahead and look at the next column. Notice this one has a negative that is closest to the spot I'm taking out. Basically, it's right next to the one I'm taking out. Therefore, I have to take the negative into account. What do negative 12n and negative 20 have in common? Hopefully you caught it. It's negative 4. That means you can go ahead and write a negative 4 on top of that column. Let's go ahead and look at the rows. The first row is 3n squared and negative 12n. Even though there's a negative 12 coefficient, it is not right next to the one we are taking out, meaning that we don't need to worry about it. So what do 3n squared and negative 12n have in common? 3n. You could also be doing the area model backward in terms of, if you already know that an n is here, and you know that this times this would equal the area of this small one, then you would know that this has to be 3n as well. So you can check your work that way. Last row, what do 5n and negative 20 have in common? You're going to take out the 5 and keep it positive because you have a positive closest to the one you are taking out. So all you would do is put a 5 on the outside there. Hopefully you see your factors, your base and your height of your area model. You have your n plus negative 4, which we would probably write as n minus 4, and then 3n plus 5. Therefore, 3n squared minus 7n minus 20 factors to n minus 4 times 3n plus 5. If you want to check your work, super easy. Just go ahead and distribute this out using any of the methods we learned for multiplying polynomials. It should equal your answer. Here's the fun part. I want you to fully factor these two trinomials. You can use strategies we have learned in this section, or you may even need to go back to your initial factoring section and use some of those strategies first before factoring the trinomials. Pause the video, and when you think you have them both figured out, go ahead and restart. So hopefully you had a chance to look over these two problems and figure out the answers. Let's go ahead and talk them through and make sure that you got the correct answers. The first question, whenever you get a trinomial to factor, should always be, can I factor out a GCF? With these three terms, unfortunately, there is not a GCF for all three of them, so we cannot take out a GCF. Therefore, we go to either the area model or factoring by grouping. I go ahead and I put the 8x squared in the top left and the negative 45 in the bottom right. I then know that the two diagonal terms have to sum to be the middle, which is 26x. Because the leading coefficient was not 1, I have to use the AC method. Now, if you went ahead and listed out all of the factors of negative 360, that's totally fine. I just went ahead and listed the one that worked, but know that it is not bad to have to list them all out, especially until you get used to doing these more and more. I promise these get easier the more you practice. With the negative 10x and the 36x, I can then go ahead and finish filling out the area model. From there, I find the GCFs of each row and column. Again, 8x squared and negative 10x have a 2x in common. 36x and negative 45 have a 9 in common. 8x squared and 36x have a 4x in common. And then lastly, negative 10x and negative 45 have a negative 5 in common, pulling out the negative from the box nearest. This means that 8x squared plus 26x minus 45 factors to 2x plus 9, 4x plus negative 5, which we write as 4x minus 5. And that should be your final answer. Let's go ahead and look at the next one. This one is a little bit trickier because this actually did have a GCF with all three terms. In fact, I went ahead and took out a 2 right away and I was left with the trinomial of 2x squared minus 5x minus 7. This is going to be a lot easier to try to factor, and plus that 2 can just remain out in front as a separate factor. I'm going to go ahead and put the 2x squared in the top left corner and the negative 7 in the bottom right. That means that these two diagonal terms have to sum to be the middle term, which is now negative 5x. Unfortunately, a, the leading coefficient, is still not 1, so I have to do the AC method. A times c, 2 times negative 7, is negative 14. Again, feel free to list out all the factors. I happen to know that 2 and negative 7 multiplied to be negative 14 and summed to be negative 5. Therefore, I filled in the boxes of my area model with 2x and negative 7x. Finding the GCFs, this first column had a 2x in common. This one had a negative 7 in common. Going across, this row only has an x in common, and these two actually have nothing in common, which means that it would just be a 1. Every number has a 1 in common. In terms of our final answer, do not forget about the 2 that you factored out. Here's my final answer over here, by the way. So I have 2 times 2x minus 7 from the top, or the base, times x plus 1 from the height. That would be my final answer for this one. If you forgot to factor out the 2, you probably have one of your binomials with both terms that are twice as large. For example, maybe you have 4x minus 14. That's why when I first said the directions on this page, I said to fully factor. We learned about the definition for what it means to fully factor, and that's that no polynomial can be further factored. So that 2 has to come out in front for your final answer.